Okay, hello everyone. Happy to be back. It wasn't fun lying on the couch for a few days last week. I'm pretty much all better. My voice is still pretty low and maybe a little weak, so hopefully it goes okay projecting and speaking to you today. Does anyone have questions or anything that's come up last week? Yeah.
Happy Thanksgiving.
Happy Thanksgiving. Thank you. Yeah. Happy Thanksgiving to everyone. I'm American, so that's nice to hear. Yeah. Any other any other questions? Anything from the last week? Okay. So I hope you've all had a chance to look at the videos that I posted. I'll say to you that the last video that I just posted from yesterday's lecture, I would say is the most important one. It's the intro to dynamic force analysis. The preceding two videos that I posted are, I'll call them optional techniques that you can use with either static or dynamic force analysis, and they make solving problems easier. But you're not required to use them for any particular problem, but sometimes they make problems far easier to study, especially if you have links with a whole bunch of forces on them. How do you handle those cases? So check out those, the first two videos, videos from last week for that kind of idea. Dynamic equilibrium is the next topic. I was hoping to have a little demo today, which I'd pushed off till tomorrow. I'll show you a video. But today we're just going to basically finish up the concept of dynamic force analysis. And this is a pretty cool topic. It seems like it's a much more complex situation than static force analysis. But once you get into solving the problems, there's more steps to solving a dynamic force problem as compared to a static force problem. But ultimately, these new steps are not really harder than static force problems. So today we're going to go through maybe the trickiest part of dynamic force problems, and that is basically how do we substitute our dynamics and put that into our equilibrium kind of studied language. So this is maybe just a little review from the last lecture video from yesterday's lecture that I posted. Here's a link, right? Here's a link, and it has these two forces applied to it. And those are maybe applied from other links in the mechanism, something that's going on. Maybe we know those, or maybe we don't. But if you look at those two forces, you can see right away this link is not in static equilibrium, right? They're not balanced. Because there's only two forces, if they were in static equilibrium, they would have to be equal, opposite, and collinear, right, to be in static equilibrium. So at a glance, you can see it's not in static equilibrium. So that means if a link is not in static equilibrium, it must be in dynamic equilibrium. Like every link, we can treat it as dynamic equilibrium. It's this concept of basically adding a new force that compensates for the dynamics to balance this and put it back into equilibrium. So these two forces cause an acceleration on this link. And basically, you can imagine they're both pointing up to the left, so of course the acceleration is going to be up this way. And when we're talking about dynamic links that have mass, that it's accelerating, and we're going to study the dynamics of them, we want to track this center of mass, right? G, center of mass. That's the important location of acceleration that we need to track. So that's moving up this way. And the way we compensate for this now and put it back into equilibrium is we introduce this new thing called an inertial force. And it's equal to negative ma, acceleration of our center of mass. Okay, so we're going to add this force onto our link, and that's basically going to put it into what we call dynamic equilibrium. Okay, it's negative ma, so we're just going to put it at the center of mass. Okay, and I put it in white here to indicate that it's another force on our link, and it's in balance now. It's in equilibrium. So once we add this, our link is now in equilibrium. And we call it dynamic equilibrium. And the last thing I'll note about this basic case is that our link, or this new force that we added, this inertial force, is not a real force, right? It's kind of, we're making it up. It's the real forces that are applied to this link are Fa and Fb. And those cause the acceleration. That's what's happening. That's the real physics that's happening. And you'll remember what we did in the lecture before. This is dynamics, right? F equals ma. That's physics. That's our dynamics. And what we're doing here by adding this Fin, negative ma, is we're treating it like it's a force. So we have our real forces. And then we have this, some people call it a fictitious force. And that's why I put this in quotes. Because it's not a real force, but we're acting like it is. We're putting it on the left side of the equation so that they add up. Fa plus Fb plus our inertial force. Now the link is balanced. Now it's in equilibrium. So this is the concept of dynamic equilibrium. It's not the only way to study dynamics problems. You can kind of study it in this original F equals ma framework, which is a fine way to do it. But we're going to be studying it in this fictitious force framework. And the reason why I'm introducing this, and the book does the same thing, is that now our problem looks just like a static equilibrium problem. So now we treat this like it's another force that's applied to our mechanism. And we're actually going to go through a full example by the end of today's lecture about this. So any questions about our basic dynamic equilibrium concept? If you want a more full look at this, refer back to the last lecture. So okay, so we've included Fin, but I didn't include the moment if there's some theta double dot which is induced here. So I introduced that before, but today I'm going to show you a clever way to include the moment. So let's say a link experiences some theta double dot. Right? That's going to lead to this inertial moment. Okay, and the moment is equal to I, which is our moment of inertia. It tells us about how the mass is distributed around our link. Refer to the last lecture or your dynamics course from some years ago, times theta double dot. So this is like the rotational analog, rotational version of our Fin. Okay, the challenge is if we put a moment onto our link, all of a sudden it ruins these links being 2-force or 3-force links. And it makes them much harder to study in general. So I'm going to introduce today, our main topic for today is we're going to look at a little trick. So this is a all right trick here. I think that's the best description for it, of how to include this inertial moment. Okay, and I'm going to say without any moments. Right, because putting moments on links ruins our 2-force and 3-force links. So ideally, we would not put moments on there. And the idea that we're going to do is we're going to do an equivalent situation. So let's say we had a link with moment applied to it. We're going to replace that moment with a pair of forces. Right? Any moment can be expressed as a pair of forces. So think how these forces should be some pair here to get the same effect. Okay, it's a counterclockwise moment, so we need 2 forces, equal and opposite, could create that same moment on this link. So what if we did two forces like this, separated by some distance? Right? That would create a moment. Okay, and these forces are pointing at each other equal and opposite directions. So these would not create any additional force load on the link here. So this is like an equivalent representation of this moment as a pair of forces. Okay, so if we don't want to deal with moments, we can kind of replace them with a pair of forces. That's a great kind of trick we can pull to a bit simplify our problem. But rather than applying a pair of forces, we can go even one step simpler. This is like one way to replace the moment with forces. But an even easier way is let's use a force that we already have on our link, which is FIN. Right? FIN, that's our inertial force. We've already applied it to our link. So what if we could use that FIN and just offset it? Offset it. Okay, and I'm going to show you what I mean by that. So let's draw our, this is our original link here, but I'm going to give you one that has a FIN and a moment that's induced here. Okay, we have our center of mass here. And we had that acceleration. Let me get my colors going here. So our acceleration of the link. But we also have on here a moment that's applied to this. Okay, and that's basically induced, moment should be, we'll put that in white. Let me keep my color coding right here. Okay, and the green should be the theta double dot. So now we're considering if we have some theta double dot on our link as well. Okay, so that's how you could express a link that has theta double dot and acceleration with a moment and a force. But what I'm going to do is we're going to do this on the right-hand side here. I'm going to show you how instead of putting MIN, let's just offset our force. Right? If we move the force to a different location, it's going to create a moment as well. Right? So I'm going to try and create, let's say I wanted to create this MIN by offsetting this force. Right? It's counterclockwise, because MIN is negative theta double dot direction. So I want to create a counterclockwise moment. So basically, I'm going to take my force, and I'm going to slide it up or down. And I'm going to try and create that MIN. So let me just put those forces on here again. There's my center of mass. So I'm going to slide it up or down. Does anyone have a suggestion? Should I go down some or up some to create a counterclockwise moment? I see down, pointing down. So imagine if I put it down here. We're talking about moment about the center of mass, about g. So yeah, if we put a force down here instead of right through the center of mass, it's going to rotate the whole length counterclockwise. So that's right. So what I'm going to do is I'm going to go perpendicular to that force by some distance. And I'm going to put FIN. It needs to be parallel, same direction as it's supposed to be there. Okay, so you see I've offset it, right? And I've offset it by some distance. And we're going to call that distance rho. That's our little moment arm. So you may say, how do you know how much to offset it? Right, this would create a counterclockwise moment. But how much to offset it? So we're going to answer that question now. Okay, and the purpose of the offset is to create this amount of moment, right? So it needs to create MIN, which is negative I theta double dot. So that's a number we could calculate, right? We have these numbers. You could get theta double dot from your acceleration polygon. I is a property of the link, moment of inertia of the link. So that's something we could calculate, just like we could calculate A and FIN. Okay, so if we want to create this amount of moment, we'd say, okay, what's the moment induced by FIN offset. So if we take FIN and we offset it by some distance, right, this is a perpendicular distance. So it's we just offset at a perpendicular distance. So that means the moment created by that offset is just FIN times the amount of offset. And we want that to equal MIN. So that's all there is to it. And we can solve for rho, the amount of offset. Inertial force in the denominator, inertial moment in the numerator. And I'll just write those out in full here. Okay, so that's the calculation you need to do to use this offsetting method. Okay, so this is a clever little trick you can use. You don't have to do this. You could work with this left-hand case. You'd have a link with 1, 2, 3 forces and 1 moment applied to it. And you could study a link like that. It's not a 3-force link because it has a moment applied to it. An easier link to study is going to be this one. Right? All of a sudden, this particular link, we've made it into a 3-force link. And that's great. 3-force links are much easier to study than these kind of generic links where you have to come up with a different strategy for each link that you want to study. And last part you need to know is about the direction. The direction of the offset. Right? You're going to have to use your, just your looking at the link here. If you want to create a counterclockwise moment, take a look at your force and give it a try. If you're not sure how to do this, just give it a try. Sketch in a FIN, offset it over here, and ask yourselves, does that create a counterclockwise or a clockwise moment? I want counterclockwise, so that was the correct one. If I tried it up here, you'd say, oh no, that's creating a clockwise moment. It's rotating my link clockwise to move the force up to here. So that one's wrong. That's why we went with the bottom one. Okay, so you just have to use your sort of geometric look at your link. And every link's going to be different. They're going to be flipped around. So you'll have to do that differently each time. Any questions about this? Yeah?
Yes, like what would you do if, in the case where AG is equal to 0 and you have pure translation, how do you like get rid of the moment then?
So your question is if AG, this is a special case, where AG equals 0, but you had some theta double dot not equal to 0. Yeah, in that case, this is going to mean FIN equals 0. So you can't use this method to do it. Yeah, you can't use it. You could replace it with a pair of forces, but I don't know if that's really better than a moment. Because a pair of forces, probably you're going to end up with a whole bunch of forces on your link then. So in this case, I mean, in this case, your link's not that bad anyways. So it's not a probably that difficult case to handle. Yeah, you wouldn't apply this technique for it. Okay, in the book, this is sometimes referred to as inertia circle method. Cameron's going to talk about this in tutorial tomorrow as well and do some examples. We're also going to do an example for the next 30 minutes. But he'll show you sort of another way of thinking about drawing these out. You can see the book kind of explains it slightly different as well, which may help you to look at that as well. Was there another question? Yeah.
Was there like negative in front of the eye?
These ones you mean?
Yeah.
Yeah. You could put a negative there, but it's the same thing. Yeah. Yeah, and the sign of this doesn't really matter because you have to think about the direction sort of manually anyways. So just calculate this as a scalar quantity. Just calculate that as a distance, 3 centimeters, and then figure out whether you should go up or down, sort of manually. Any other questions? Okay, so let's do an example. Let's do an example for the rest of today. We're going to look at a mechanism that we've studied before, which is a 4-bar. But we're going to treat one of the links as if it has mass, and we're moving it through some notable acceleration. So we're going to consider its inertia. Up till now, we've always ignored those links. Okay, so I'm going to draw the 4-bar. Okay, so here's my 4-bar. And let's say that link 3 here, let's say that link 3 is connected to some output of this machine. And in fact, the shape of link 3 is pretty large. It's a large link. Kinematically, we could represent it like this. But to capture where the mass is, we're going to need to add sort of a coupler point here. So this is the simplest way of representing that the center of mass of this link is way up here. Okay, and I didn't draw the true shape of the link. It's kind of weird that its mass is up here. You can imagine maybe it's made out of plastic and it has a big weight up there. Or maybe the true shape of the link, yeah, is really big. And this represents the kinematics and dynamics of this link. And we need to know some properties of that link, notably its mass and its moment of inertia. So let's say the mass is 0.5 kilograms and its moment of inertia 2.5 times 10 to the negative third. And our units are kilogram meter squared. Okay, so that's the properties of that link. And let's assume that links 2 and 4 have pretty low mass. Or maybe their acceleration we calculated is pretty low, and we've chosen to ignore those. So we're going to neglect everything else about this mechanism. We'll also neglect the weight of the links. You may say it's weird to study a link's inertia, but not its weight, because they both depend on mass, right? Inertia and weight both depend on mass. Maybe let's consider the link, the whole linkage is operating in the horizontal plane, operating like this, okay? So we'll neglect the weight and everything else. And our task is going to be, let's say that there's an input here. We have a motor here on link 2. So our task is, let's find the motor torque, which is required to move this mechanism through some desired motion. And if we have an inertial load, this mechanism could be balanced even if there's no other loads on the mechanism. So let's say the goal here is going to be to create some velocity in the mechanism. So let's say we want to create some velocity, input velocity, 120 radians per second on link 2. And this is actually a similar 4-bar that we've studied before. And we're going to assume that we've already solved acceleration polygon. Okay, we know how to do that. Let's assume that we know the accelerations of all the links. And we've found acceleration of these points, and in particular g3 and theta 3 double dot. These are things that we've found already. I'm going to draw them on here. Okay, so we found g3 is accelerating this way. Okay, and we found the theta 3 double dot is rotating counterclockwise. So link 3 has a rotational acceleration counterclockwise. Okay, so this is our situation. And this is a pretty realistic case. And up till now in the course, this is a typical kind of input that we've worked with. We've said theta 2 dot equals something as an input to the mechanism, right? That's often an input we gave. And we kind of ignored how that happened, how that was generated. And now we're getting to really what does the motor have to do to create that velocity at this snapshot in time. This is a typical input from an acceleration polygon problem that we've had before. So let's find this out. Oh yeah, we need the amplitude of these as well here. Let me sneak them in at the top. Acceleration of g, 250 meters per second squared. Acceleration of that point, and theta 3 double dot, 750 radians per second squared. Okay, squeezing everything on the board here. So those are the inputs that we need to know for this mechanism. So we're going to go through our solution now. And basically, we're going to use this technique. So we're going to need to calculate FIN. We're going to need to calculate MIN. Now we're going to calculate rho. Right? And we're going to treat that. Right now, it's not in equilibrium, right? It's not balanced. Because we have this moment applied, but there's no other forces on the mechanism. Right? So we need to apply that FIN. That's going to be our balance on this mechanism. Okay, so dynamic problems, calculate FIN first. Okay, you always have to work with your acceleration of that center of mass of that link. Right? Link 3 has lots of points. It has these other points B and D here. On link 3, that's not where the mass is. The mass is at G3. So we need the acceleration of that point, G3. Okay, so we have all these numbers already. 250 meters per second squared. Okay, so this comes to 125. And newtons should be kilogram meter per second squared. Comes to a newton, 125 newtons. Okay, so we could put that onto our linkage, onto our mechanism if we wanted. I'm going to do it for now. Maybe you don't want to do it in your notes because we're gonna move it later. But it's going to be equal and opposite, or not equal. It's just going to be opposite direction to AG3. So if we wanted to also put MIN, we could put FIN right there. But we're going to move it in a second and handle MIN and FIN in one step. Okay, so that's MIN or FIN. Let's do MIN next. Negative I theta double dot. This is easy enough. I is 2.5 times 10 to the negative third. These moments of inertia are weird. It's hard to get an intuition about those numbers. Okay, times our rotational acceleration, which is 750 meters per second squared. I can't do that one in my head right in front of you here, so I calculated it before. 1.88. And our units come out to newtons times meters. Okay, we need to know the direction. Right? It should be negative theta double dot direction. So I'm going to sort of manually figure that out. Theta double dot is counterclockwise, so our MIN should be clockwise. And this is what I've suggested to you before. To make sure you're keeping track of things, my preferred is to keep moments positive once you calculate them. Just write the direction on there. That way you don't have an ambiguous answer. Great, so we could, your option 1, which I don't suggest, is to put MIN here. Right, clockwise, it's an applied force and it's applied moment, and you could proceed with a equilibrium analysis problem then. But the issue is link 3 is ruined as a 3-force link. We know there's going to be a force here at B, a force at D, and FIN. So there are 3 forces. So we have hope of making link 3 a 3-force link. But if we apply MIN to it, it ruins that. So what we're going to do is we're going to do our new offset trick. So let's do our offset trick. But we need to calculate rho. We need to calculate rho. And I'll actually put it right in here. Since we have our equation, we'll figure out how much offset to give here. Okay, so we just do MIN divided by FIN. We have those two numbers. Units should come out to distance, right? Rho is a distance. FIN come out to 125 newtons. Okay, we get out with 1.5 centimeters for rho. 1.5 centimeters. So that, if we want to do our offset method, if we want to use FIN offsetted to create the moment, MIN, we need to offset at 1.5 centimeters either up or down. Either up or down. And we're trying to create, what is it, clockwise, right? MIN. Trying to create a clockwise MIN. So which way do we want to offset it? And then I'll take a question or two. If we want it to create positive clockwise moment, do we offset it this way or this way? Give it a try in your head. If I moved it here or moved it here. Yeah, so this one here would create counterclockwise, so that one's no good. This one here is the right one. So we want to move it down. I want to move it down this way. And the amount of distance that we move it is 1.5 centimeters. So you take your perpendicular line here. You march over 1.5 centimeters. That's rho. And that's where we're going to apply FIN. So we have that amount of offset, and we apply FIN there. And once we do that, we don't need MIN anymore. We've accommodated that. We've created the moment artificially by offsetting our inertial force. That's the offset there. Questions about that? Yeah. Oh, yeah. So this is theta double dot. It should be, yeah, radians per second squared. Yeah, thanks. But yeah, I was obviously not looking at those when I wrote Newton meters. I just knew that it should be Newton meters. Yeah. Other questions about what we've done? So at this point, we have a nice mechanism for analysis. We have FIN applied to link 3. It's applied off at this weird position, but that's okay, right? Forces can be applied to links at any location, even off the link. You can extend it back to the link if you want. It's really like the line of action is right along there. And we'll study that link just like it's. Now you can forget about dynamics and say there's just a rope there pulling on that link with that amount of force. FIN, 125 newtons. Okay, so we're going to go through the last few steps here. We're just going to look at the solution for this linkage, which will be a bit of a, I guess, review of an equilibrium solution to finish up this problem. And as always, when doing equilibrium force analysis problems, you need to go link by link and draw out the links and do your free body diagrams. You're doing yourself a big disservice if you skip the step. Okay, link 4 doesn't have any weight or inertia on it. We ignored those things. So there should be a force at either end. Force from 3 and force from 1. So this link 4 is a 2-force link. Great, 2-force links we see all the time. Easy to study. These two forces should be equal, opposite, and collinear. Now let's try and guess, so we don't have to correct it later, are the forces pointing out or in? The load on my mechanism is this one. This is my load, right? FIN, it's pulling up. So just think, imagine FIN was really big. I come in here and pull up on a string, FIN pulling that way. Is that going to push down on link 4 or pull up on it? Yeah, I'm pulling up. So the whole mechanism's kind of being pulled up in tension. So a good guess, I think, for link 4 is that link 3 is pulling up on link 4. Pulling up on it. We'll find out if that's correct. If you ever make a wrong guess, you'll find it later when you do a force polygon, and you can correct it. But that's my guess. OK, that's link 4. Let's move on to link 3, the next one. OK, I'm going to draw as accurate as I can here. Okay, at this point, the center of mass is not really important up here, right? We've already done the dynamics. So now that we're doing the rest of the force analysis problem, you can kind of forget about the center of mass. It's not really important. I just drew it on there so we can keep track of our link. Here's our force applied. $125, right? There's our force applied. Here at B and D, we have forces from links 2 and 4. So we have from 4 to 3. And from 2 to 3 is applied here at B. So this looks just like other problems that we've solved now, right? F4,3 should be equal and opposite to F3,4. And we don't know its magnitude, right? But we know its direction. F2,3, we don't know anything about that. Link 2 has a moment applied to it. So link 2 is not a two-force link. So that one we don't know yet. F2,3 is at B, but we don't know where. But this is enough to solve a three-force link problem now. So we'll remember back to our steps, solving three-force links. All three forces should intersect at a common point. So I just extend the two that I know and find that intersection point, which we call K. And that helps us find the direction of F2,3, which also needs to point to K. And F2,3 needs to go up or down. Can you guess which one? I see some hands waving. Right, this link needs to be balanced. It needs to be in equilibrium. We don't have dynamics anymore. We just have, it's treating it like a static problem now that we've put this FIN. So this force, it looks like it's going to create a clockwise moment, right? So F2,3 must be kind of countering that, balancing that. So that would be my guess for F2,3. We'll see our polygon, and we'll see if that's correct. So let's do the polygon over here. Okay, the one that we know is FIN. So let me put that on first. I would draw it as 12.5 centimeters if I wanted a huge one on my page. Okay, 125 newtons. And now we need to put these other ones on. You can choose to put it at the head or the tail. I'm just going to choose randomly F4,3. So F4,3 goes over here on this dotted line somewhere. F2,3, I'm going to put at the other end. So okay, so we have our triangle, our force triangle. And remember, they need to go head to tail. I'm just going to move this stuff out of the middle, these labels. Okay, head to tail means those two should be pointing like that. They go around in a circle, round in a circle. Okay, so those are the three, and I can use my ruler now to measure these. I'll just look at these. This one, F2,3, I'll say is 105 newtons. And really our goal, right, let's think about our goal now. We need to find the moment on link 2. That's the motor torque input here. So really what I'm trying to go to is link 2. So we don't even care about F4,3, but you could estimate that one as well. We'll say that one is 65 newtons. Okay, so we're ready to go to our last link. Our last link is link 2. Okay, and at this point, right, the problem looks basically identical to ones that we've studied before. Okay, link 2 has the moment 2 applied from the motor. Here at B, we have this force F2,3, which I didn't even mention. Looked like we guessed it right. down and to the right. F23 is down and to the right. Okay, so let's get that direction on there. You'll use your triangles to do this. I'm eyeballing it. Okay, 3-2 should be opposite from 2-3. So I put that arrowhead on wrong. There we go. And we know the magnitude, 105. 105 newtons. Okay, so we're going to solve for M2. So just like we've done before, let's do moments about O2. And we'll say counterclockwise is our positive values, just so we keep track. So we have M2, and F32 is creating a positive counterclockwise moment as well. So it has some distance offset, which will be this distance here. Right, that's the moment offset of F32 about O2. So it turns out that the value is going to be negative, right? This tells us we're going to get a negative number, which makes sense, right? To balance this force, you'd need a clockwise moment to balance that, to keep link 2 in equilibrium. So that's what it means by giving us a negative number here. Okay, so F32, yeah, 105 newtons. Just checking if I was right about that. And our offset distance, D32, you'd measure on your scale diagram. I just made this example up, but I'll tell you, let's say it's 1.5 centimeters measured on there. Okay, so we get our moment 2. It comes out to 158. And units should be newtons times centimeters. And the direction, it's negative, which means clockwise. So if I want to write it like this, maybe it's best I should actually flip this around on my diagram as well. If I'm just working with positive moments, probably best to flip it around. So that's my final answer to the problem. If I set my motor to apply this much torque, maybe you could look up on the motor data sheet how much electrical current to give it to create 158 newton centimeters. You'd calculate, I need to apply 1.2 amps of current. That current will create this input velocity. It'll turn that motor at 120 radians per second, if we made the right assumptions about this problem. Okay, so this is a dynamic problem. Our mechanism didn't have any external loads besides the weight or the mass being accelerated around. Okay, the other way to think about this problem would be moment 2 is creating that acceleration at G3, right? So there's different ways that these problems could be stated as well. And a few examples are given in the problem set that you're studying here. I'll just point you to one other example. So Cameron's going to do one tomorrow, a nice example, in Cameron's tutorial. And the book gives another nice example as well. So check out 8.9. So if some things were a little hazy to you in today's lecture, I went through all this. Check out the book example and Cameron's tutorial tomorrow for a little bit more about that. Any final questions? Great. So tomorrow I'm going to give some concluding remarks on force analysis. And then we're actually going to start our next topic. And I'll give you a little review or a preview of the rest of the semester, last few topics here. Thanks, everyone. See you back in person tomorrow. Yeah. Happy to be here, too. Thank you. Yeah.